Now that we've familiarized ourselves with working with radical expressions, we can also begin to utilize those tools we've discussed in the previous videos to solve radical equations. And outside of a few nuances that are specific to radicals, these will largely follow the same basic principles of solving any type of equation. For example, if we consider something like the square root of x equal to 16, our goal here, just like it always has been, is to isolate x. And we'll be able to do that by undoing the operations that are being done to x. So right now in this case, the operation being done to x is taking its square root. We can undo that operation per se by squaring both sides, right? So if we take the square of the square root of x and the square of 16, then the square root of x times the square root of x, right, or square root of x squared, is just x itself, and 16 squared is 256. And so we find that x equal to 256 is a solution to our equation. Right? And this is something that we can check and verify, of course. If we were to plug 256 back into our equation, then we have the square root of 256, which is 16, equal to 16, which is of course a true statement. So a lot of these big picture ideas that we've discussed when it comes to solving equations still apply now. The difference is that, at least in some cases, when we do this operation of squaring both sides, we can actually introduce solutions that aren't really solutions. So what do we mean by that? Let's consider the equation x is equal to 5. If we were to apply this same sort of reasoning and we were to square both sides, say x squared equal to 5 squared, let's watch what happens, right? We could simplify this to say x squared equal to 25. We could subtract 25 from both sides so that we are setting x squared minus 25 equal to 0. We could factor the expression x squared minus 25, giving us x minus 5, x plus 5, since of course that's a difference of squares. And then we can use the zero factor property to solve for when x minus 5 is equal to 0 or x plus 5 is equal to 0, giving us x is equal to positive 5, which does match what we had at the beginning, or x is equal to negative 5, which does not match what we had at the beginning, right? What we've done here when we squared both sides of our equation was actually introduce another variable x, right? We had just one x here. We add in an x times x when we square it here, so we're potentially introducing another solution. X minus 5 in this case, though it does satisfy this equation, it doesn't satisfy our original equation. And so while this technique does work for the most part, we do have to be careful and check the solutions at the end to make sure that they satisfy not only the equation that we've created by trying to solve it, but the original equation that we started with too. And so for example, let's see if we can take a look at solving for when the square root of 6x plus 7 minus x is equal to 2, so we can get a feel for how this plays out. Now, in order for us to do what we did here, in order for us to square both sides of the equation in the easiest way possible, it's going to be important that we have our equation set up in this way, in this format that we have here, right? Where we've got the square root just on its own on one side equal to anything else on the other side. That way when we do square it, we can remove the radicand. And so we'll start here by isolating the radical on one side. So in this case, if we start with 6x plus 7 minus x equal to 2, we can add x to both sides. This gives us the square root of 6x plus 7 on the left equal to x plus 2 on the right. Then from here, we can square both sides, and that's going to allow us to eliminate the radical from the left-hand side. So we'll take the square of the root 6x plus 7, and we'll also take the square of x plus 2. Now it is important here that when we do this, we are squaring the entire side of the equation rather than just any term individually, but we can square x plus 2 and FOIL it out as we have been in previous videos. And so if we do this, this will give us 6x plus 7 on the left and x plus 2 times x plus 2, right, x plus 2 squared on the right. Now again, let's remember here that this could potentially introduce extraneous solutions. So this could introduce extraneous solutions. So we will have to check this later, but this will at least allow us to get to a place where we can use previous techniques to solve for x, right? And so from here, we'll solve the equation as we previously might have, meaning we'll expand the right-hand side by FOILing. So we'll leave 6x plus 7 on the left, and then on the right, this will give us x squared plus 2x plus 2x plus 4, which simplifies to x squared plus 4x plus 4 when we combine like terms. We can then subtract the 6x and the 7 from both sides so that we set our equation equal to 0. This will give us x squared minus 2x, right? Plus 4 minus 6x gives us minus 2x, and minus 3 because 4 minus 7 gives us minus 3. And so we have a quadratic equation which we can solve. As we know, there are multiple ways at which we could do this. We could use the quadratic formula, we could complete the square. I think in this case, the easiest way is probably just to factor, right? We can look at this expression on the right and realize that we have two numbers that multiply to -3, which would be -3 and +1, which also add to -2, right? -3 plus 1 is equal to -2. And so we can factor this as x minus 3 times x plus 1. Then using the zero factor property, this tells us that either x minus 3 is equal to 0 or x plus 1 is equal to 0. And I'm running out of space a little bit here, so I'll just come up over here to say that tells us either x is equal to 3 or x is equal to -1. And normally this is where we would stop and this would give us our final answer, our final solution. But again, we want to remember here that that step that we took previously when we squared both sides might have added an extraneous solution. And so it is going to be important for us to check and verify that both of these or either of these work. And so our last step will be to check to verify the solutions. And so we found x equal to 3 and x equal to -1. So if we check for x equal to 3, we would plug that in to our expression. So 6 times 3 plus 7, the square root of that, minus x, or minus 3, equal to 2. If we multiply 6 and 3 here, we'll get 18 plus 7 minus 3 equal to 2. If we add 18 and 7, we'll get 25 minus 3 equal to 2. If we take the square root of 25, that gives us 5 minus 3 equal to 2. And of course, that does indeed equal to 2. And so since we have a true statement at the end, we can confirm that 3 is in fact a solution. Similarly, if we check -1, we can plug in 6 times -1 plus 7 minus -1 and see if that is equal to 2. 6 times -1 is going to give us -6 plus 7. The minus -1 will become plus 1. If we add -6 and 7, that's going to equal just 1. And if we take the square root of 1, that's also going to give us just 1. And so on the left-hand side here, we have 1 plus 1 or 2, which again, in this case, does equal 2. And so we can confirm that -1 is also a solution. So in this case, both of the values that we found do work. They are both solutions, but that's not always going to be the case, as we'll see in our next example coming up. But at least for now, this will allow us to conclude that our solution is -1 and 3. But let's try to apply that same process to solving the square root of x plus 2 plus the square root of 3x plus 7 equal to 1. because as we'll see here, there are sometimes situations where we do have to eliminate one of the extra solutions. Now, with an equation like this, you might be noticing right off the bat here that this one is going to be a little bit different, because that first step where we wanted to isolate the radical isn't exactly going to work in the same way, right? We know that because these are not like terms, we can't just add them together and put them all under the same radicand. So instead, I'll write isolate the radical in quotes here, because what we'll do is try to balance it out so one radical is on one side of the equation and the other radical is on the other side of the equation. This way, when we square both sides, we'll at least take care of eliminating one of them. And so in this case, that's going to give us the square root of x plus 2 equal to 1 minus the square root of 3x plus 7. Now this isn't perfect like the last case, but at least this time, when we square both sides, we'll be able to eliminate at least one of the radicals, right? This square root of x plus 2. And so if we do that here, and we square our left-hand side, and we square our right-hand side, well, on the left-hand side here, that's going to give us just x plus 2. On the right-hand side here, we're going to have to be a little bit careful to make sure that we FOIL. And so this will equal 1 minus the square root of 3x plus 7 times 1 minus the square root of 3x plus 7. Then from here, being careful to FOIL this out, we'll multiply the first term by the first term, or 1 times 1, which gives us 1. We'll multiply the outer terms, so 1 times negative root 3x plus 7, or just negative root 3x plus 7. We'll multiply the inner terms, also minus square root of 3x plus 7. And then we'll multiply the last terms, or root 3x plus 7 times root 3x plus 7, which gives us plus 3x plus 7. And this is a little bit messy to work with, but we can use the algebraic tools that we've discussed in the recent videos to work to simplify this a little bit. We'll keep the x plus 2 on the left, and then on the right, we can combine like terms with the positive 1 and the positive 7, giving us a plus 8. We can combine like terms with the root 3x plus 7s, giving us minus 2 root 3x plus 7. And then we also have this 3x term. Now you might be wondering how exactly that's gotten us closer to where we ultimately want to go. And the reason is because now we've gone from having 2 radicals in our equation to having just 1. Since we have just 1, if we essentially just repeat the same process, isolate that radical on one side, then by repeating this process, we can get rid of that one as well. And so from here, we'll repeat going back to step 1 to isolate the radical, and then to step 2 where we'll square both sides. So specifically here, if we subtract 8 and subtract 3x from both sides, that's going to give us x minus 3x, or minus 2x, 2 minus 8, or minus 6, equal to negative 2 times root 3x plus 7. From here, if we divide both sides by negative 2, on the left we'll have negative 2x over negative 2, or simply x, and minus 6 over minus 2, or simply plus 3. And on the right we'll have our isolated radical of root 3x plus 7. Here, if we square both sides, we can get rid of that radical, giving us x plus 3 squared, or x plus 3 times x plus 3 on the left, and 3x plus 7 on the right. Now if we copy this and bring this up onto a new page, some of these are going to take a few more steps than some of the problems we've worked with in the past, but that's okay. Here we can continue with the same process we've been working with so far. We can FOIL x plus 3 times x plus 3, giving us x squared plus 3x plus 3x plus 9, or more simply, x squared plus 6x plus 9, if we combine like terms. We can subtract 3x from both sides. We can subtract 7 from both sides, giving us x squared plus 3x plus 2 equal to 0. And we can ultimately factor this expression to utilize the zero factor property to solve this equation. we can recognize here that 2 times 1 is going to equal 2, and 2 plus 1 is going to equal 3. And so our factors would be x plus 2 and x plus 1. Utilizing the zero factor property, this tells us that x plus 2 could equal 0, or x plus 1 could equal 0, which we can solve for -2 or -1. But again, we're not quite done yet, because if we go back here, at either of these steps where we squared both sides of the equation, we could have potentially introduced extraneous solutions. Extraneous solutions. And so we'll need to check both of our solutions to make sure that they do actually satisfy that original equation here. And so we'll need to check both solutions to verify. If we start with x is equal to -2, we'll have the square root of -2 plus 2 plus the square root of 3 times -2 plus 7 equal to 1. And if we simplify this, -2 plus 2 is going to give us 0. 3 times -2 is going to give us -6. The square root of 0 is just 0. -6 plus 7 is equal to 1. And so we have the square root of 1, or 1, is equal to 1. Because this statement is true, that confirms that this is indeed a solution. If we check x is equal to -1 though, what we'll have is the square root of -1 plus 2 plus the square root of 3 times -1 plus 7 equal to 1, which as we simplify will give us -1 plus 2, or the root 1, plus the square root of 3 times -1, or -3, plus 7. Square root of 1 is just 1. The square root of -3 plus 7 would be the square root of 4, and the square root of 4 is 2. So here we have 1 plus 2, or 3, is equal to 1. Right, and we know of course this is not true because 3 does not equal to 1. And so this confirms to us here that x is equal to -1 is an extra solution. It doesn't actually satisfy our original equation. And so here we have an extraneous solution. And so instead of saying our solution set is -2 and -1, in this case we can say, therefore, we have a solution set of just -2. We'll get rid of that extra solution, -1. So these problems can get a little tricky sometimes, and that's okay. We'll be careful with the algebra because it does require a lot of working with square roots and their properties, and we'll be aware of the potential extraneous solutions that we add when squaring both sides to help solve. It may take some practice, but ultimately this outlines the process here. And if we stick to that process, being careful along the way, I know we'll be able to get it. And so I hope you found this video helpful. Let me know if you do have any questions or if there's anything else I can do to help. Otherwise, as always, I hope you have a great rest of your day.